Do you know about spatial hearing? Let me give you an example. You're on the street. You hear a bike rushing past on your right. You step aside without even thinking. That's your spatial hearing. But spatial hearing is much more complex than this simple example. Imagine you're in a crowd bar with live music and friends. You can talk with your friends, right? You know exactly who is speaking and understand what they're talking about. This ability to rapidly localize events in the environment and navigating our surroundings is called spatial hearing. But for your brain, locating a sound is actually a complex computational challenge. Why? Because sound location isn't directly mapped onto your sensory organ, the cochlea. Welcome to Back to Science, and to the new series, The Sound, Space, and Brain. We are breaking down the comprehensive review paper, Cortical Mechanism of Spatial Hearing by van der Heyden and colleagues. They reviewed neurophysiological, neuroimaging, and computational modeling studies of how the mammalian auditory cortex represents sound location. They proposed that this cortical representation emerges from recurrent processing taking place in a dynamic and adaptive network spanning primary and higher-order auditory regions. Understanding how your brain locates sound is more than academic curiosity. It is crucial for helping people with hearing loss regain spatial awareness. But first, we need to understand the fundamental sound cues the brain has to work with. Note that our focus on this series will be on encoding sound location in the horizontal plane. For decades, auditory neuroscientists have examined the neural mechanism of spatial hearing. Research shows that spatial cues are extracted and processed to a large extent in subcortical structures. However, lesion studies underscore a crucial role of the auditory cortex in neurosound location encoding. The complexity of this process is increased by the need of compute and integrate information across multiple location cues and sound frequency ranges. The anatomy of the head, torso, and pinna, the external ear, introduce differences in the time and intensity of the sound wave arriving at the two ears. These differences are our primary cues for horizontal localization. Because the ears are separated in space, a sound reaches each ear at a slightly different time. This difference is known as the interaural time difference. At low frequency, this timing difference can also be expressed as an interaural phase difference, reflecting the phase shift of the sound wave between the two ears. In addition, the head partially blocks sound energy, producing a head shadow effect, known as the interaural level difference. Beyond these binary cues, each ear also receives unique spectral filtering by the outer ear and the head, providing monaural spectral cues. This information helps distinguish sound elevation and front-back position, resolving front-back ambiguities in horizontal plane. The classic description of how these cues are used is the Duplex theory of spatial hearing. The theory suggests that the contribution of each binary cues depends on sound frequency. ITDs are considered most relevant for low-frequency sounds, and ILDs for high-frequency sound. However, this theory has been challenged by findings showing that each type of binary cues contribute to sound location across a wide range of frequencies. For instance, ITDs conveyed by the envelope of high-frequency sound and ILD present in the low-frequency sound can still be used for localization, especially in reverberant listening settings. Furthermore, there's no clear relationship between neurotuning to sound frequency and to ITDs or ILDs. ITDs modulate the firing rate of neurons tuned to high frequency, not just low frequencies. In this adaptive figure from a study, the x-axis shows the horizontal azimuth and the y-axis shows the neuron's firing rate. This line represents the condition where only ITD varies, while this line shows responses when ITD is fixed. For this comparison, we can see that while low-frequency neurons rely purely on ITDs, high-frequency neurons also show clear ITD-driven changes when a competing sound is present, evidence that ITDs modulate even high-frequency activity. Neuroencoding of ILD in the chinchilla midbrain is frequency invariant. As shown in this adaptive figure, each neuron's response curve has a midpoint, an ILD value where it switches from weak to strong firing. When this midpoint value and response range are compared across frequencies, they showed no consistent change. This means that neurons in the midbrain represent ILD with a similar sensitivity at the both low and high frequencies, even though physical ILD cues themselves vary strongly with frequency. This indicates that binaural cues are relevant across a wider range of frequencies than predicted by duplex theory, and neurons encode both cue types regardless of their frequency tuning properties. The physiological range of ITDs is determined by head size. For example, the maximum ITD in human is about 700 microseconds, while in cats it is 300 microseconds. For periodic sounds, time differences are expressed as IPDs. Note that larger time difference result in phase ambiguity. When the broadband sounds are filtered by the cochlea into frequency domains, the delay is processed as IPDs for those individual components. The physiological range of IPDs is determined by two more factors than head size. Sound frequency. Low-frequency tones have smaller maximum IPDs than high-frequency tones. Temporal resolution. The upper limit of physiological range of IPDs is set by the auditory system's temporal resolution, that is, by highest frequency at which auditory nerve fibers and neurons in the subcortical pathway can reliably phase lock to the sound waveform. The physiological range of IPD is the function of sound frequency, head size, and the temporal resolution of the auditory system across mammalian species. Okay, we established that spatial hearing is a computation challenge based on integrating binaural ITD and ILD cues with spectral cues. The classic duplex theory is challenged by findings showing these cues are relevant across a wider frequency range, and their neuroencoding is often frequency independent. The physiological range of the crucial ITD-IPD cues is strictly determined by head size, frequency, and temporal resolution. Next episode, we move from these basic cues to the cortex itself, characterizing the key properties of cortical neurons. We will explore how spatial tuning in the auditory cortex is mostly contralateral, stronger for sound coming from the opposite side. Then we will see how an active, goal-oriented behavior can actually sharpen a spatial receptive field of neurons. Which aspect of cortical spatial hearing did you find the most interesting? Leave your thoughts in the comments. And don't forget to like and subscribe for the next episode of Back to Science.